So creating good models is really an art, and this is why I make the comparison with a painter, right? You have the real world, and then you have the model that try to capture as much as possible the reality. And for us in constraint programming, creating a good model is choosing the right variables, choosing the right domains, and posting the right constraints. Okay, so let's start and make some painting with constraint programming. And usually for the same problem, you might have different possible models, different set of variables, different domains, and different constraints. And unfortunately, depending on the kind of model that you are designing for your problem, it might impact dramatically the solving time. And so usually you have to experiment to decide which model is the best for solving a specific problem. But with some experience, you will come to models that you already know that might be more efficient than other ones. I want to illustrate the art of modeling by studying a problem that is called steel-mill slab problem. And the model that I will introduce to you is really a non-trivial model. So for that specific problem that has been studied for like 10 years, people usually came with more simple models at the first time. And then gradually this model was discovered and was the most efficient one for solving that problem. So the problem is the following. Steel is produced by casting molten iron into slabs, okay? And the slabs are represented by the colors here. Oh, sorry, they are represented here by the knots. There is no color in the slabs. So we have three possible slabs here, okay? Slabs, this is where you put molten iron. So basically, you will fill here, you will fill the slab with molten iron, okay? And then, okay, like this. And then after that, you will cut it, okay? You will cut and you will split into different parts. And this is what you will do. And the way you will cut the molten iron is because you have some orders that customers ask for, and you need to molten the iron to meet the customer orders. And the orders are represented here, okay? And they have some colors, okay? You can assume that the color, for instance, is the customer, okay? And so this customer asks for 3 orders with this specific length, and then you have the red customer and you have the green customer. And so the 8 is what is represented by a weight here. And so you receive in input n orders. Each order has a specific size or weight. And the goal is to decide which slab you will produce. And you want to minimize the total loss of the steel that you have produced. So for instance, this is one solution. You would choose 3 times this slab. Okay, so this slab is used 3 times, and then this slab is used once, and this one is used 0 times, and this one is used there. And then you will assign the orders to the slab, and this part that you see here, they will be lost because the slab will be completely filled. Then you will cut the orders, and so this is a lost part. And the goal is to decide which slab you will use, such that the way you will assign the orders to the slabs will minimize the total loss. Okay? So that's the problem that you need to solve. What could be the decision variables? So first, let's describe the input data. So the input data is n orders. Then you have the color of each slab. And you have the weight of the order I, okay? And each slab has the different slab capacity, okay? You have sigma different number of slab capacities, and you have n different type of slabs, okay? I forgot to mention one constraint is that you cannot assign more than 2 colors to a same slab, okay? So you cannot assign more than 2 colors to a same slab. And this is the model that we will do. So these are the decision variables. What I will do is that I will decide for each order, and these are really the decision variables. I will decide for each order, I, the slab that will be attributed to that order. And so the domain of these variables is assuming that I have n slabs, is from 1 to n. Okay. Then I will also have the weight. This is the weight of the orders attributed to slab J. Okay, this is the total weight of the orders attributed to slab J. So assume that I have a slab here that I'm using that has been assigned this order, and this order. Okay, this one is 5, this one is 7, and this one is 4. Then the Pj here is equal to 12, 16. Okay, so Pj for this slab J is 16. I will use the index J for the slabs and index I for the orders. And so Lj is the minimum loss of the slab attributed here. And so which slab should I use? So assume that I have the slabs available are this length and this length. It's quite obvious that if I decide to assign orders with weights 5, 7, and 4 to this slab, I will preferably use this one, okay, so that my loss here is minimized. Okay, so Lj is this. Lj is the minimum loss, okay, by choosing the slab with minimum capacity, but the capacity should be larger than the total weight of the orders that I have chosen to assign to this specific slab. And the goal here is to minimize the total loss. So the total sum over all the slabs of the loss of each slab. Okay, so this is the intuition for the main decision variables. I didn't introduce yet any constraints, and this is what I will describe now. So first, how do we compute the loss of a slab? Assume that I will create a small example, and everything will become clear, hopefully. Assume that I have available 3 different slab capacities. A slab with capacity 5, 8, and 10. Then I can pre-process the array by assuming that the slab will be filled at different levels. Okay, I can pre-compute this array, and this array corresponds to the 8 of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So, assume that the total load of this slab is equal to 6. If the total load is equal to 6, then the slab that will minimize this loss is to choose the one with a capacity of 8. Okay? And if you choose the slab of capacity of 8 for and you will fill it up to 6, you have a loss of 2, which is represented here. Okay? Now, if you have a slab that you fill with a weight of 9, the only slab that you can choose is this one, is the slab with capacity 10, and the loss will be 1. Okay? And so you pre-compute here an array that will tell you at every index that represents the load, what would be the corresponding loss. Okay? And so L of I, in this pre-computed L of, let's say, Lj, is equal to the loss if the slab filled in with weight Lj. Okay? We already met something like that before. It should remind you a very familiar constraint that we already studied, which is the element constraint. Okay? And the element constraint is exactly what we need, because we need to index this L array, which is an array of integer, by a variable that will model the total weight. Okay? So the loss of the slab J is equal to the value that can retrieve in this pre-computed array, but at the index Pj, and Pj is the total load variable. Okay? Pj is the weight of all the orders that you have assigned to the slab J. Okay? And this is really the very nice idea in this model, is the way you will compute the minimal loss for each slab. You can retrieve it by indexing this pre-computed loss array with the variable Pj, and Pj represents the total weight assigned to slab J. Okay, so now let's state the constraint to make sure that Pj represents the total weight assigned to the slab j. And so for that, we will simply use this sum constraint. We will say Pj is equal to the sum over all the orders, okay, such that the order is assigned to j, order I is assigned to slab j, of the weight of this specific order. This kind of constraint is so frequent, okay, that we have a global constraint to model that constraint. This global constraint is called the pack or the bin packing constraint. This is the weights, okay, these are the weights of all the n orders. This is the where, okay, where do you place them, okay, and this is the load of each of the bin, okay. This is called a bin packing constraint because it will model something like this. It will model something like this, in which you decide in which bin you place the orders, and okay, so in that case you have 0, 1, 2 bins, and so the domains of the where variables would be 0, 1, or 2. You decide in which bin you will place them. So these are for the domains. These are the weights. The weights is for each order the specific 8 of them, and this will be the total 8. So this will be the total 8 of each of the bins. Okay, each of the 3 bins. We call that a pack or a bin packing constraint.